Recording, rolling. It is Monday, February 5th. All right, a lot of guys just turned in your electromagnetic spectrum and optics quiz, so I'll get those graded for you guys. I gave you guys new posters that you guys see them hanging up on my room. Actually, I got two categories of posters. The red banners over there on that wall, that's these right here related to thermodynamics and heat transfer. Got laws of thermo. Today, main focus is going to be this thermo PowerPoint. Right? So you see a lot of concepts show up here. Right? Eventually, I'll get you guys some textbook puzzles that correspond to stuff you guys got to see today. Right? And then on the back side is another set of posters. These are the orange banners hanging in front of me right here, related to material properties and engineering. So it's like density, ideal gas law. We got fluid properties, Pascal's principle, Archimedes, Bernoulli. Stress and strain. If you go into engineering, you'll see that all over the place. I got concrete, steel reinforced. All right. So in time, gonna work our way towards that, but let's get going on this thermodynamics. All right, guys, ready for PowerPoint? PowerPoint. All right, so switch screen over here. Oops. Boom. All right, thermodynamics, heat transfer. All right, so start with the temperature scales. So how can you measure how hot is something? And what's the idea behind this? There's this kinetic energy theory of temperature, which is if you touch something and it's hot or it's cold, right? There's some kind of thermal energy transfer, right? It's a new form of energy that we're going to look at, like this thermal energy, right? If you get down to the molecular level, maybe different molecules are vibrating at different rates, right? But if you sort of take like an aggregate average of how fast are molecules vibrating, right? That's related to the temperature, right? So is it room temperature? Is it hot? Is it cold? Right? There's something like that, right? And how can you quantify how hot or cold something is, right? Well, here's three different systems, and I think the historical ordering of when these were devised was, I think Fahrenheit was first, and then Celsius, and then finally Kelvin. So let's go in that order, right? Right. So Fahrenheit system, we still use in the States for weather. This one that 32 degrees is defined as the point that water freezes, and 212 degrees is where water boils. Right? Now, this water boiling point, this is only true for 1 atmosphere of pressure. So down here at sea level, that would be true, right? But if you change the pressure, then that goes out the window. We'll look at that later. Look at a phase diagram for water for different pressures too, right? But if you're at 1 atmosphere of pressure, this would be true. Right? There's some crazy history behind like where those numbers come from, but at least that was again, I'm pretty sure that was the first scale that was come up with, like at least a way to measure temperature, right? Then metric system becomes more universally accepted, and everything is, well, let's have anything like logical, base 10, and say, and also properties of water are a lot of ways embedded in the metric system. Like you guys remember, for example, the original definition of a kilogram is if you take a box that's 10 centimeters by 10 centimeters, 10 centimeters, fill it with water. Right there, that was the original kilogram. Okay, and so let's make 0 degrees the freezing point of water and 100 degrees the boiling point of water for Celsius. Right, and it's really only true at 1 atmosphere, but let's just keep that condition. Right, I think actually this guy originally Celsius was devising this scale the other way. So let's have 0 for boiling and 100 for freezing. It would just be all topsy-turvy, upside down, right? Anyway, we got this, which I think makes a lot more sense anyway. Right, so okay, so now we got a translation from Celsius to Fahrenheit, back and forth. You can go, right? So I'll just say this verbally, or you guys can see it on that poster over there. You guys have it on your thumbnails if you want to convert. Right? Let's say you're overseas one summer and they say, "Oh, it's a jolly 26 degrees outside." Like, wait, what? What does that mean? Right? Can I have that in American? So take your 26 degrees Celsius, multiply by 9/5, and add 32, and then that'll translate it back to Fahrenheit. Right? So there you go. Go back and forth. Right? Right. Now, both of these systems, Fahrenheit and Celsius, they can go into the negative values. You can have negative degrees, but that doesn't really mean that there's a negative of anything. It's like, what does that mean? The atoms are vibrating in a negative way? No, because these are just relative scales, right? They just have to do with like properties of water. There's certain values that we've set, certain benchmarks, right? But those are just relative scales, right? Now, is there a coldest you can go? Yes, and in each of the scales, you see what those numbers are. Obviously, these thermometers here are not exactly to scale, right? They skipped a bunch of numbers, right? But in terms of the Celsius scale, you can go down to about -273, and then a little bit of change there, right? But there's no such thing in the universe as -274 degrees Celsius. That's just not a thing. When you get down to about -273 degrees Celsius, you get so cold that the vibration of the atoms like slows down to near zero, and you actually undergo this weird phase change where it's no longer a solid; it becomes something called a Bose-Einstein condensate, and it has these like weird quantum properties, right? It's really weird, right? But you could call it like absolute zero. And now I'm introducing this last scale called Kelvin, right? Where they actually do define 0 Kelvin as absolute zero, like absolute zero temperature, right? So this scale, Kelvin, has the advantage of being an absolute scale versus the other two are relative, right? So you can, plus or minus, just like relative scale, right? But Kelvin is an absolute scale. So it only has positive numbers on it, right? And you have to use Kelvin when you're applying, let's say you want some proportion change in temperature. You want to say, like, what's going to be the effect? Later on in this presentation, you'll see ideal gas law, for example. Suppose you have a balloon and you heat up the balloon. Do you guys think it's going to cause the balloon to expand? Yeah. By how much? Okay, well, now that's a math question, right? Well, how much proportionally did we increase the temperature? Do we increase the temperature by like 10%? Well, then I bet the balloon is also going to expand in its volume by 10% too, right? Which is true. But the math you have to apply has to be in Kelvin, right? For if you're scaling up the temperature by some percentage, right? It has to be in Kelvin or by some ratio, right? And then you see where the numbers land there. Kelvin and Celsius are going to be scaled the same in the sense that a change in 1 degree is the same, right? So a change in 1 degree Celsius is the same as a change in 1 Kelvin, right? Notice I'm not saying degrees Kelvin. It's a little technical thing. You just say Kelvin, right? Right. So the change is the same. Therefore, 273 Kelvin is the freezing point of water, and 373 Kelvin is the boiling point of water in one atmosphere. Okay, you guys got that? Okay, so there you go. There's temperature scales. Right, that'll be important later when we're doing some math. Okay, let's look at these laws of thermodynamics. Okay, so sort of made a poster version of this. Right, we've got these 4 laws. Let's go through each one of these. Right. And then the main ones that I'm going to focus on are the first and the second laws. That's the ones that I really care about. If there's any final exam questions about these laws, it would be on the first law and the second law. Right? Well, let's check them all out. So the zeroth law, this says if 2 systems are in thermal equilibrium with a third system, then they're in thermal equilibrium with each other. Okay, what does that mean? Right, so that means that they would be at the same temperature, and there's therefore going to be no heat transfer. Right? So if you touch an ice cube and it feels cold, then there's a heat transfer from your hand into the ice cube, and it's warming up the ice cube. If you touch some surface and it's really warm, it's more than your body temperature, right? Well, now there's a heat transfer from like that object into you. Right? So if there's a mismatch in temperature, then the heat wants to transfer from heat is a transfer of thermal energy, right? So the thermal energy wants to go from the hot object to the cold object, right? And that process will continue until they're matching temperature, right? And then say this object has the same temperature as this object, and this is the same as this, right? Then this would have the same temperature as that, right? So very basic. There you go, right? So thermal equilibrium just means it's the same temperature, therefore there's going to be no heat transfer, right? Right. First law of thermo. Sometimes this one's called conservation of energy, which you guys learned back last semester. So you cannot create or destroy energy as a quantity, some number of joules, right? You can't create or destroy that, right? What you can do is change forms. So you guys saw it last semester too, right? It goes from, say you drop a ball from the top of the Leaning Tower of Pisa. It goes from potential energy to kinetic energy, right? Maybe something like that, right? And then this week we're going to bring in also thermal energy. So if there's some energy that goes into maybe heating something up. So an example of this that you guys are going to see pretty soon, I found a textbook question that has to do with a waterfall. Suppose there's a waterfall of some height on Earth, and it's dumping water over and like into some pool of water at the bottom. Right? Do you guys think when that water splashes into that pool, it heats up a little bit? Right? Heats up a little bit, right? So how much? How much does it heat up the water at the bottom? Due to splash, right? Well, you could say go from potential energy, right? Based on the height of the waterfall, something to do with like MGH, something, right? to thermal energy, something to do with like MC delta T, right? The delta T would be like the change in temperature, right? That heats up, right? Ooh, I bet if the water falls twice as high, it's going to heat up the water twice as much, right? It might be like a fraction of a degree, but there's going to be a right? Like energy is conserved, and you can transfer different types. Last semester we focused on mechanical. This week we're going to start bringing like thermal energy, right? Right, guys, good so far? Right. All right, this second law. Ooh, okay, this one gets pretty deep and abstract, and there's a lot I want to say on this. And I've got a few slides coming up about this too. Right? So I'm going to spend quite a bit of time talking about this one. Right? So what does this say? This says the entropy of an isolated system always increases. Okay, what does that mean? Right? This has a lot of implications. So one meaning of this is that heat naturally flows from hot to cold objects, right? So if there's a hot object and cold object nearby each other, right, you would expect the thermal energy to transfer from the hot to the cold. So that's what heat is, right? It's a transfer of thermal energy, right? Now, this is a statistical law of nature, right? So if you get down to like the atomic scale, if you're just focusing on individual atoms, every once in a while you'll see this law be broken, right? But in the aggregate, when you're talking about like trillions of atoms, then this pretty well holds true, right? All right, so now there's like a time order of flow, right? And that's another interesting thing about the second law. This is a law that I think was uncovered in the 19th century, right? When people working with like steam engines and trying to figure out how exactly does the energy move around, right? Run up against certain barriers. Okay. So yeah, they found that there was this the physics before that is somewhat symmetrical, right? Like if you look at Isaac Newton saying like momentum is conserved during collisions or something, it's like, okay, well, how do you know like which way the collision happened if it's conserved? There's the same momentum before as after, right? And I guess in this class, so one thing we do is say, oh, well, the kinetic energy would tend to decrease, right? But the energy doesn't disappear, right? Right. So how can you say like things happen in one particular process, one particular direction, right? And statistically, you'll see this to be true, right? Again, there's a lot more I want to say on that, but let me say that for some other slides, right? You can quantify entropy in like joules per Kelvin, right? Weirdly enough, so there's an equation that's going to pop up pretty soon, right? So let's look at the third law real fast, and I'll switch slides here. Right, so third law, I've seen different wordings of this. So this wording says entropy of a system approaches a constant value as the temperature approaches absolute zero. Okay, I guess that's kind of interesting. It's not going to be a huge focus in this class, so I don't know if that's going to come back so much, right? Right, but let's look more at that second law. Right? Okay, oh, here's like thermal equilibrium, right? Now this is also related to the second law, so let's look at this. Suppose you have a hot tank sit next to a cold tank. Say 100 degrees Celsius water and 0 degrees Celsius, or let's say maybe 99 degrees Celsius water and 1 degree Celsius water, right? Extremely hot next to extremely cold, right? And you just leave that sitting side by side for like 5 hours and come back later, right? Well, you would totally expect it to be a heat transfer from the hot to the cold, and they're eventually going to reach this thermal equilibrium, right? Now they're same temperature, right? Something like that, right? If they started out the same mass water, then it'd be like right in between, like 50-50, something like that. Okay. What you would not expect is what if you start off with two lukewarm tanks of water, like 50 degrees Celsius, 50 degrees Celsius next to side by side, right? And then come back 5 hours later and spontaneously a bunch of thermal energy has gone from the right to the left. So now you have one tank that's hot and one that's cold, right? That'll never happen with like trillions of atoms, right? Like maybe like 2 atoms possibly randomly every once in a while, but not like trillions of atoms. You understand, right? Right. That's another implication of the second law of thermodynamics, right? This is like arrow of time. Things happen in one direction, not the other. Now, closer to the end of this presentation, I'm going to start talking a little bit about air conditioning and refrigeration, which you might say, wait, doesn't that go from the picture on the right to the picture on the left, right? Like if you have a bunch of like warm air, it's like, oh man, it's so hot in this room. We need some air conditioning, right? Okay, there's some process you can have. Such a recent technology, like even when my parents were going to school, they didn't have air conditioning in schools, right? Right. So how do you take a bunch of relatively warm air, right, and get some of it cold, right, and then transfer out the heat energy to the other side, right? Okay, well that's an energy intensive process, right? It's hard to make that happen, right? Which you can make it happen, but there's a larger thermodynamic process at play, right? So let's look at this process of entropy. Right? All these slides are related to this idea, right? So what is entropy? Entropy is a thermodynamic quantity representing the, okay, so here's another perspective here. An unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system, right? So let's say you buy a gallon of gasoline, put it in your car, right? Now there's energy in those chemical bonds in the gasoline, right? Then you combust that gasoline and makes the car go. There's some mechanical energy, right? But there's also maybe some energy that went to heating up the engine, right? The engine feels hot. There's a thermal loss there, right? You had to plow against the air drag, right? There's a little bit of energy loss there, right? So there's these other forms of energy that in quantity is the same as the number of joules that started off in that gallon of gasoline, right? But they're lower quality of energy, right? And you can't just go around and like regather all that lower quality energy and keep making the car go again, right? Um, and do you have an equation come up next slide? Yeah, okay, so here's some terms here. Q is going to be like thermal energy. So a delta Q is like a heat transfer, right? Delta Q is heat transfer, right? If you divide that by the temperature that this process happens at, right? And this has to be an absolute temperature in Kelvin, you can get delta S is the change in entropy, okay? So entropy will increase as the universe moves forward in time, right? For processes, right? Right. So let's go back to this again, right? It was a physicist working with steam engines and different engines back in the 19th century, where they uncovered this perspective of physics too, right? But here's another perspective, something about like a degree of disorder or randomness. There's this maybe sort of analogy, but it's still part of entropy, right? Has to do with like ordering things. So if you have low versus high entropy systems, right? Let's look at the sandcastle, right? So yeah, there's like a time order to the sandcastle they made. Right. So suppose go to the beach, you build this sandcastle. That's a highly ordered form of sand, right? And then you come back 5 hours later, and okay, great, it's a giant pile of sand. Maybe that was to be expected, right? You leave it there long enough, it's eventually gonna wash away with time, right? What you would not expect is like, what if you just started with a random pile of sand, and you come back 5 hours later, and it's spontaneously turned into a sandcastle? Like, will that ever happen? Like statistically, no, right? Statistically, it's never going to go from the picture on the right to the picture on the left spontaneously, right? Now you might think, well, hold on a minute, I can force it to do that. Right? I can like take my arms and like move individual sand grains around until I take the picture on the right and force it to turn that picture on the left, right? And kind of like air conditioning, you're taking some small system that has high entropy and you're forcing it into low entropy, right? It's the same thing with air conditioning and refrigeration, which might make you think, wait a minute, wouldn't that therefore somehow break the second law? Because the second law says that entropy of an isolated system should always increase. Here, I'm taking the sand and I'm ordering it to a sandcastle. That's decreasing the entropy. So, what's the problem with the second law of thermo? Right? And the bigger picture here is that it takes effort on your part to move those sand grains around, or in the case of air conditioning, there's a bigger process. You have to like plug your air conditioner into the electric grid to make this thing run, right? So that, let's go back to the sandcastle. You're building the sandcastle, right? You're moving your muscles around. Okay, so you ate breakfast in the morning, then you go to the beach to build the sandcastle, right? And in moving your muscles around to move the sand around, the increase in entropy in your muscles outweighs the decrease in entropy by building the sandcastle every time. Right? So no matter how orders and how much you decrease the entropy by building the sandcastle, the entropy in your muscles will always increase more than that, right? So that the entropy in the universe in total always increases. Right? Again, this is more of a statistical law of nature than anything else. So is it possible that maybe some crazy technology 1,000 years from now we've sort of found a way to skirt around this second law of thermo? Maybe it's kind of it's one of those laws that's almost a way like asking to be possibly be broken, but yeah, other than like individual like two atoms at a time, we've never really on a statistical basis seen that happen. Right. So here's another slide, also on second law of thermo, right, again related to entropy. So let's look at this. Second law of thermo states that this is what I've been saying, but here's kind of spelled out. the total entropy of an isolated system, say the thermal, okay, and what do I mean by entropy, right? That's the thermal energy per unit temperature that is unavailable for doing useful work, can never decrease, right? So it can increase, or I guess it could stay the same, but it cannot decrease for the whole universe, right? Right, so that's this equation here. I was just pointing out this equation, but let's look at this again. So here's your heat transfer, delta Q, right? That could be like you have a hot tank next to a cold tank. The heat transfer is going to spontaneously go from the hot to the cold. You would expect that, right? Divide that by the temperature this is happening at, right? And you'll get a change in entropy, right? Now, I guess we got two heat transfers. It's away from the hot and it's into the cold, right? So take this heat transfer, divide by that hot temperature, say it's 99 degrees Celsius hot, right? But remember, I have to transfer that to, I have to translate that into Kelvin, right? So anyway, it's going to be a large temperature, right? There's going to be some small decrease in entropy is what it would be. Actually, this red box here, this hot sink is actually decreasing entropy. Wait a minute, I thought that would violate the second law of thermo, right? But careful, because that's not the full picture. This cold sink, this blue box, is gaining the same quantity of energy, right? That's what the delta Q is, the same quantity of energy, right? But it's at a lower temperature. So that's, as a fraction, is a higher number. So the increase in entropy of this cold sink outweighs the decrease in entropy of the hot sink, like I said, right? So this ds over dt says what this means is, this is kind of calculus notation, right? As time moves on, right? So with the transfer, with the passage of time, right? The entropy of, and I should throw a subscript on that says universe. The entropy of the universe will always either increase or stay the same, but it cannot decrease. Right? All right, you guys got that? Okay. Right. And then here's another example. Second law of thermo is, so you fill a balloon with air, right? Now you have kind of highly ordered air molecules in this high pressure balloon, right? Then you open the balloon and all the air escapes, right? Which is a process that you would expect to happen spontaneously, right? Okay, so now that those air molecules escape into the wider atmosphere, and now that is a higher entropy state, right? But you wouldn't expect that process to spontaneously happen the other way. If you just have a balloon just lying around, it's not just going to spontaneously fill up into a high pressure balloon, right? That's never going to happen spontaneously. Right? You can force it to happen, right? But however much you're decreasing the entropy of the balloon system by filling it with air, with high pressure air, right? You're increasing the entropy of the universe overall, because that comes from your lungs, right? Your lungs are increasing entropy more than it's being decreased by the balloon. So yeah. Okay. Right, you guys good so far? Right, I know there was a lot on the second law and entropy. Okay, so it's really abstract concept. But get a little bit of math of that. All right, let's look at heat transfer. Here's three main categories of heat transfer. Some textbooks have like another one that might be kind of a subcategories, but I'm just going to focus on these three. Okay, so conduction, convection, and radiation. Okay. Hopefully you guys learned these in a science class in the past. Hopefully this is some kind of review. Let's hit them all. So conduction is heat transfer by direct contact of surfaces. In this example, maybe this pot's been sitting on this stove range, so maybe this handle is made out of metal, so it's really hot. When you touch that metal handle, now it's thermal energy transferring from the handle to you. Okay, there's conduction, right? So direct contact with surfaces, right? Let me skip over to radiation, because I think my next slide is convection, right? Let's look at radiation, right? Radiation, this is heat radiating possibly through the vacuum of space. It could, right? That's how sunlight gets to Earth, right? Goes through the vacuum of space, right? Not necessarily through a vacuum, though, right? So maybe you have an, if you put your hand nearby the stove range, don't touch it, right? But if you put it nearby, it's like, ooh, I can feel it's really warm. There's heat radiating from the stove range, right? Or if you have a window on your oven, right? You turn on the oven, right? You put your hand near the window. It's like, ooh, I can feel the heat radiating out, right? So, so you don't need direct contact, right? It's just electromagnetic waves, right? Maybe so electromagnetic waves, maybe infrared mostly. And then convection. This one is by bulk movement of fluids. Right? So bulk movement of fluids. Right? Fluids might refer to liquids or gases, but there's some kind of bulk movement, right? Maybe because of a temperature differential, right? Like if I have this pot of water on the stove and I turn on the stove, the bottom of the water is hot. The top of the water is close to room temperature, relatively cooler. There's a temperature differential. Okay, well, that's going to initiate this convection process where it's trying to reach a thermal equilibrium by transferring energy. And how does it do that? By physically moving these fluid molecules around. Here's your convection, right? But there's a whole sunshine state standard about, I'm supposed to show you guys this, so hey, here's a good spot for it, right? Ocean currents. So here's some ocean currents that have been stable for, who knows how many tens of thousands or more years, right? So what's driving these currents, and why do they move the way they do? Right. Well, one of the main drivers is temperature differential for convection currents. Okay? So you have warm water near the equator, cold water near the poles. Right? Well, we got a temperature differential. It wants to try to match equilibrium, right? And so it's going to set up these convection currents, right? That's one of the drivers of these ocean currents. Right? Now, there's some other drivers too. How about salinity differences? Like how salty is the water? Do you guys think that the water near the equator is evaporating faster than at the poles? Kind of makes sense too, right? There's more solar flux at the equator, right? Does the salt in the salt water evaporate, or just the water? How about just the water, right? Ooh, if just the water evaporates, doesn't that leave behind like saltier water? Well, now you have a salinity differential, right? Oh, because that's another driver of these ocean currents too, right? And then the third driver I've read is wind. I don't know how significant that is to those other ones, but that's what I read too, right? So wind, right? Look too, there's did you guys see it in the northern hemisphere? It looks like these currents are going pretty well clockwise for the most part. And then down in the southern hemisphere, it's pretty predominantly counterclockwise. Ooh, do you guys remember last semester there was Coriolis effect? You guys remember Coriolis effect? That's what would make those currents go those particular directions, right? And so like here off the coast of Florida, got this convection current going up to taking a bunch of warm water like nearby Florida and taking it all the way up to northern Europe. You guys see that? Let me ask you guys. Here, I'm gonna flip my screen back. I got a trivia question for you guys. Can you guys imagine where Britain is on a map? Like England, Scotland, and Wales, right? And then if you track straight over to North America, what's the same latitude as Britain in North America? Huh? Canada? Yeah, like Canadian Shield. All right, let's go look at this map again. Yeah, you're right. Trek straight left or straight west. Yeah. Right. Whoa, are those radically different climates? Like Britain is, I mean, kind of cold but temperate, right? Versus here's the Canadian Shield. This is like tundra, right? So why is there? I mean, the same latitude. Because of this Gulf Stream, right? This Gulf Stream is taking all this warm water and dumping it onto northern Europe, right? Right. All right. Let's look at this heat transfer curve. Okay, here, I got a story for this one. So we're going to do, right? Let's say you take an ice cube out of the freezer and you put it on the stove. Okay, what's the whole process for it to go from an ice cube to steam, right? So here's that story. Okay? So on this graph, I got increasing heat energy to the right. You know, so you can always go to the right on this graph. Okay, so that's like putting something on the stove. It's transferring heat energy into, well, in this case, we're going to start off with an ice cube, right? And then going up on this graph is increasing temperature. And notice there's some places where the temperature actually gets stuck for a while. You guys see that too, right? Let me ask you guys too, have you guys seen this in chemistry? Who's seen this in chemistry? Seen this in chemistry? Raise your hand. Yeah? Is that about half the class, I think? Right? Yeah, a lot of, yeah, a lot of this presentation, a lot of students, like, have you seen this in chemistry? And, yeah, about half, so, right? Some of you guys just might be a review. Some of you guys, well, here you go. So here's the story. We take an ice cube out of the freezer. That's like right here. Maybe it's like negative 10 degrees Celsius. I'm just going to use Celsius for the story, right? So negative 10 degrees Celsius, right? Put it on the stove. Now, putting on the stove, we're going to the right on this graph. So that's putting energy into that ice cube, right? Now it stays solid cube until it hits, bam, this point right here. And then it starts to melt, starts to undergo this melting process, right? And if you have a thermometer on this ice cube, it started negative 10 degrees Celsius, hits 0 degrees Celsius. When it hits 0, it gets stuck at 0 degrees Celsius, right? And it stays that way until the entire cube melts. And this whole flat line right here is a mixture of ice water. If you're on the far left, it's all ice. If you're on the far right, it's a puddle of really cold water. It's just all melted, right? If you're kind of in the middle, well, that's like having a glass of ice water. Because if you have a glass of ice water, I can tell you what the temperature of that ice water is. It's 0 degrees Celsius every time, right? Because it's a mix of ice and water, right? And then, yeah, it's always going to be somewhere along this line, right? And then adding heat energy to it doesn't actually increase the temperature until it all melts away. Right? Right. And then when it does melt away, right, now the temperature can start to increase again. So now we're at liquid water, right? So increase until you hit finally 100 degrees Celsius. Right? I'm assuming we're at 1 atmosphere of pressure. So we're down here at sea level, down in Florida. Right? We'll talk about pressure change later, but let's just stick to 1 atmosphere of pressure at 100 degrees Celsius. It starts to boil, right? And again, the temperature gets stuck. So if you have a pot of boiling water, you're like, oh man, I want to boil this egg faster. Maybe I should just turn up the flame. Well, it's not really going to do you any good, right? Because the temperature of the water doesn't actually change. All it does is just boil away the water faster, right? But it's not going to change the temperature any faster, right? So it's not going to cook your food any faster, right? Now, unless you have a pressure cooker, right? If you increase the pressure, then now you can warp this curve a bit, right? But if it's like an open pot, right, then open to 1 atmosphere, then your boiling water can't go over 100 degrees Celsius, right? Now, once it's all boiled away into steam, and you could somehow keep heating that steam can go over 100 degrees Celsius. That's okay, right? And they're on this part of the curve, right? You guys got that too? Right. Now, what about different properties of these different lines? Now, my whole story was something to do with water, right? What about other materials? About other materials have similar looking curves, right? But maybe different materials have like different slopes of these lines. Let's call it specific heat capacities, like the reciprocal of the slope. Right? We'll look at that. Right? Or what about the lengths of these flat lines? Like how much energy does it take to completely change phase? Right? It's called heat of heat of fusion down for this bottom one to melt something, or heat of vaporization to boil it. This is top one. Okay, something like that. Let's look at here's the equation that goes along with that. So let's read the music of these equations. So delta Q is a transfer of thermal energy. I call that heat. Right? Transfer. Okay, so I'm trying to heat up this. What started out as an ice cube, right? Okay, so M is how much mass. Like what was the mass of the ice cube I pulled out of the freezer? Okay. Delta T could be the change in temperature, right? So that could be like it's like a vertical change on this graph, right? Which again, only 3 out of the 5 parts of this graph can actually undergo a temperature change, right? That's during the solid, liquid, or gas phases, not the change, right? Right. And then the C could be the specific heat capacity, right? Which is the reciprocal of the slope of this line. So think like, what's the slope of that line is related to that, right? So how much energy does it take to change the temperature of something by 1 degree Celsius, right? Water has a huge specific heat capacity compared to most other materials. It's really, really, really hard to change the temperature of water, right? Like if you have a pot of water on the stove, right? Like a metal pot and water, right? Turn on the stove. I bet that metal pot's going to heat up in a hurry, right? Because metals have a low specific heat capacity. That's that C, right? But that water, it might take a few minutes to boil because it takes forever to heat up water. Right? Water has a huge specific heat capacity. Really hard to change the temperature of water. Right? Now, what about for those flat lines where there is no temperature change, where you're either melting or boiling or something, right? You're trying to change phase. Right? Well, that's what this bottom equation is for. So you can still be pumping heat energy into it, thermal energy, heat, right? That's the delta Q, right? But maybe I'm more interested in like how long is that flat line, and that's what this delta H is. So that could be basically the length of this melting line or the length of this boiling line. Okay, you guys got that? Okay. Well, I've got some textbook questions. We're going to navigate those formulas to figure out like how much energy does it take to like, take that ice cube and completely boil it away. Right? You could answer with those 2 equations. Right? Go through different parts of this. Right, okay, you guys got that? All right, see what we got next here. Oh, here's different specific heat values. Like here's water. Got 4,186 joules per kilogram Kelvin. Right. The other value you see is like 4.18. That could be joules per gram Kelvin. You might see that too sometimes. Okay. And then here's heat of fusion and heat of vaporization. Say like water. Maybe you're melting an ice cube here, but maybe you're boiling it here, something like that, right? How much energy for that line, something like that, right? I think I had a video here that's not playing. Don't worry about that, right? One of these days, I got a whole day of Paul Hewitt demos for you guys related to a bunch of these concepts. Right? Now let's look at a bigger picture because that whole curve I was looking at. I'll go back to this one, right? This whole curve right here. This might be at a specific pressure, and then you change the pressure, and maybe this curve shifts around a little bit. So let's have pressure as a variable, and now we got this whole pressure, temperature, phase diagram. So let's work our way around this. So going to the right, I see increasing temperature. So the top is listed in Kelvin, the bottom is listed in Celsius, and they're off by the value of 273, but they're otherwise scaled the same, right? And notice it's scaled linearly. So it looks like it's going up by 50 degrees Celsius at a time, or you can say 50 Kelvin at a time. That's the same idea, right? Did I say this was for water specifically? I think I did, right? Okay, so this is just for one material. This is just for water. Change the material, you get a little bit different looking phase diagram, right? Okay. Let's look at the vertical axis, pressure. And notice this one's scaled logarithmically, or you could say exponentially. I say 1 Pascal, 10 pascals, 100 pascals, 1,000 pascals. Look, it's go by a factor of 10 at a time. You see it? Okay, so, and then what are some special values on this graph, right? Well, I see two vertical red lines. This is at 0 degrees Celsius and 100 degrees Celsius, okay? And then I see one horizontal red line, and that's at 1 atmosphere. Notice it's just above 100,000 pascals. Oh, 1 atmosphere. It's gonna be like 101,300 something pascals. Okay. Our entire life experience is pretty much in the vicinity of my mouse cursor right there, right? 1 atmosphere, room temperature, right? If I say, how do you freeze water or boil water? Probably the immediate way is, throw it in a freezer or throw it on the stove, right? But do you guys see another way to also freeze or boil water without changing the temperature? Can you do that? By changing the what? The pressure, right? Because what happens if you take water and you throw it in a vacuum chamber? What's it gonna do? Boil. Yeah, it's gonna boil away. If you touch that boiling water in a vacuum chamber, is it gonna scald you? Is it hot? No, it's not hot. It's room temperature. Actually, it gets colder, but we'll talk about that in the coming days, right? It loses heat energy. This boiling process is a process that will dump heat energy out of it. It's gonna cross this line though, right? From a liquid to a vapor, right? And what if you go the other way, right? What if you go into like the clouds of Jupiter and keep going like deeper, 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 and you get crazy increased pressure? Do you think at some point it's gonna turn into ice? Yeah, some point. Okay. Now the different categories of ice. You guys see these Roman numerals, right? Some places it's hexagonal, like snowflakes are hexagonal, but some places it's not. Some places more like a cubic type shape. It's kind of weird too, right? Okay. Hey, can you go straight from a solid to a vapor? Is that possible? Yeah, right. Can you guys think of any materials? I can think of one that might commonly, say in just room temperature, go from solid to a vapor. What's going to do that? Dry ice. Yeah, you guys got it. Dry ice. Okay. What is the chemical dry ice? What is that? Carbon dioxide. You guys are right. Right again. Woohoo. Carbon dioxide. Right. Carbon dioxide. Yeah. So it can be in like a solid form. Right. And did you guys know what the process is called to go straight from a solid to a vapor? Starts with an S. Sublimation. Yeah, that's it. So, oh man, you guys are 3 for 3. Man, getting a hat trick there. Yeah, sublimation. Yeah. Okay. Ooh, how about this? Okay, that's why dry ice is dry, right? It never actually gets wet. Ooh, goes straight from there to there. Right? How about you guys this point right here called the triple point? Right? Ooh, can you have all 3 main phases at same place, same time? Right. Now for that one, I have a video queued up. Let's take a look. Right. Now, I saved this video. It says water, but it's kind of a lie. I thought it was water. I came across this many years later after I downloaded it, and I forget what chemical it is. It's not actually water though. It's something else, right? But I bet it will look kind of like this. Right? They're going to reach the triple point. Right now, it looks like it's liquid form. Oh, there's some ice right there, right? And I wonder if we can get this to boil, because triple point, all 3 main phases should be in the same place, same time. I wonder what boiling snow would look like. What would it look like if there was like boiling snow? Would you guys like to see some boiling snow? Whoa, ooh, there it is. All right. Yeah, there's a triple point of whatever chemical that is. Right? Ooh, boiling snow. Fun times. Physics. Okay, yeah, and then this doesn't really play, so you're right. All right, let's look at ideal gas law. Show of hands. How many guys learned this in chemistry? Learned this in chemistry, guys? Only a couple guys. All right. Well, all right. Here we go. Let's go to this. Say I got this balloon roped off, right? And I'm focused on 3 main properties. There could be some pressure inside. I'll call capital P. It has some volume. I'll call capital V. And there's some temperature. I'll call capital T. Right. There's also some amount of gas molecules inside it. Maybe I'll call it N. Refers to that, right? And there's this constant R to tie everything together, right? Now, put it all together, you get this ideal gas law. Pressure times volume is number of gas molecules times the absolute temperature, and this has to be in Kelvin, right, to make this work. And then R is just a constant to tie everything together. There's different values for R depending on what units you're working with. I listed 2 values of R down here, right? Now, this whole ideal gas law is really a combination of 3 predecessor laws you can put together: Gay-Lussac's law, Charles' law, and Boyle's law, right? Which focus on these just 2 variables at a time, keeping all else constant, like ceteris paribus, right? Suppose you kept the volume constant. I'm going to focus on Gay-Lussac, right? Which maybe a balloon is a bad example for that. Suppose you had a tin can full of beans. Can you guys imagine that? You have a tin can full of beans. You put that on the stove, heat it up. Is that tin can at some point going to explode? You guys think? Okay, so as you increase the temperature, the pressure goes up, right? In fact, it's a direct proportion. If you double the temperature, you double the pressure. But remember, you can only say that if you're counting temperature in an absolute system like Kelvin, right? You have to be using Kelvin. It doesn't make any sense to have that in like Fahrenheit or Celsius, but whenever you're applying this law, have your temperature in Kelvin. It has to be, okay? There's some proportion you're scaling it up or down, okay? Charles' law, let's go back to the balloon. Let's say you heat up this balloon. Do you guys think this balloon is going to expand? Keeping the pressure constant, that would be true, right? In fact, if you double the temperature, that will double the volume. But it has to be an absolute temperature, right? Okay? If you increase the temperature by 10%, the volume increases by 10%, right? And finally, Boyle's law. Suppose we're keeping the temperature the same, constant, right? But what if you press on the sides of the balloon, make the balloon smaller? As you decrease the volume, is that increasing the pressure at the same time? Yep, if there's a fly flying around the inside, right? Feel the pressure going up as the volume goes down. There's an inverse relationship between pressure and volume, right? Okay, so put those 3 laws together, you get the ideal gas law. Okay, you guys got that? The boom. So I've got some textbook puzzles about that. We'll navigate that when we eventually get to it, right? Had some Paul Hewitt videos there, but we'll save that for Paul Hewitt Day, right? Refrigeration. Okay, now this is the one, really recent technology. How can you sort of force lukewarm air to split cold and hot so you can get something cold out of it? How do you cool things down? It's easy to heat things up. Right? You just light a fire, boom, combust something. It's easy. People have been heating things up since like caveman days, right? But how do you cool something down? Well, that one's hard. That one's tricky, right? And so here's the system. We're gonna high pressure superheat gas. We're gonna take some excess heat and like dump it out into the atmosphere. We'll have something relatively cooler. We're gonna like fan across that so that we can absorb any external heat from the external environment, right? And then route it through the system, right? And here's your either air conditioning or refrigeration. You can call it either one, right? Now, okay, got a few of those. Just get right. Have you guys ever gone through an old part of town and maybe see a bunch of air conditioning units hanging out the windows, right? Maybe this building was built, I don't know, let's call it like 1920. This building was built before air conditioning was like in vogue, right? Now, why sit the air conditioning units outside the windows? Why not just sit the air conditioning unit in the middle of the room and run it? Right? Because it wouldn't actually work, right? How about this? Let me tell you guys one of your final exam questions right now. I'm going to ask you guys this on your final exam, right? Suppose you have a refrigerator just sitting in the middle of a room, and you leave the door open all day, right? And close your apartment door. You come back, a few hours later, right? And all day, this refrigerator's been dumping cold air out the front, right? What happens to the temperature of the room after a few hours? Does it get colder or hotter? I'm going to say it's going to warm up the room. Going to warm up the room. Get warmer, right? Going to warm up the room? Yeah, that's what I would circle on the final exam. It's going to heat up your room, right? Why? Because the cold air dumping out the front is only part of the story. The other part of the story, to go back to these slides, is, okay, so here's the cold air dumping out the front of the fridge, right? Don't forget that there's another half of this process, and the hot air is being dumped out the back of the fridge. If you reach it behind your refrigerator, I bet it has a bunch of hot pipes out the back of your refrigerator, right? And so you got cold air out the front, hot air out the back, and then it all mixes together. You might say, okay, well, maybe it's a wash. Maybe it just doesn't change temperature at all, except that this is an energy-intensive process. You have to have the fridge plugged into the wall. And the entropy from this process is increasing like crazy, right? Maybe it's smaller out the front from the cold air, but it's increased like crazy out the back, right? And so overall, because it's an energy-intensive process, it's going to overall heat up the room. Okay, so all these air conditioning units, if you ever buy a separate air conditioning unit, you have to hang it out the window like this. That's the only way it'll work. because you have to dump the hot out the front so that the cold air can dump into the room. Okay, think about that. All right. Let's look at there's a few thermodynamic cycles. Okay, Carnot is a famous one. Let me play a little bit of this Bill Nye. Oh, is it not gonna play? Let me see if I can. Well, see if I can dig up Bill Nye real fast. Bill Nye, where's
Stirling engine, named after the Stirling brothers, who invented it. Got a patent in it.
guys? Where's the lights? Lights. Oh my God. Ooh. Transferring heat energy into mechanical energy. All right, there's a little bit more to this, but I might play this one another day. All right, you guys have a good day. See you guys on Tuesday.